Here are the top 5 machine learning algorithms and how you can actually apply each one in real life. Imagine that you're sitting across from a loan officer at a bank waiting to hear whether they'll approve your new credit card. On their screen, you're not just a person or a name, but actually a set of numbers and facts pulled from your history. How much you earn each year, how old you are, how much debt you already carry, how often you pay your bills late, and so much more. And behind those numbers is an even bigger archive of everyone who came before you and what happened to them next. Some people paid on time for years, some slipped into occasional missed payments, and some stopped paying altogether and defaulted. And the bank's problem is to figure out, given everything they know about people like you and how things turned out for them, what should they expect will happen if they give you this card. And though it may not seem obvious, the secret tool they turn to here is machine learning. So let's break down the 5 different models they may use and for what exact purpose. Maybe the first question they look at is very practical. For example, if we approve this person, what credit limit makes sense? Here the bank is trying to predict one singular number. They want to avoid giving you a credit limit so low that it annoys you and a limit so high that it exposes them to too much risk. And a linear regression model is perfect for this. Essentially, they are treating your safe credit limit as a kind of blend of your weighted features. The bank obviously understands patterns like people with higher income and stable employment tend to manage higher limits, and people with more existing debt or late payments tend to need lower limits. So, under the hood, the model builds one equation where each feature pushes the line up or down by a fixed amount. It tries many combinations of those shifts until it finds the one equation that best matches what turned out to be sensible credit limits for thousands of past customers. So once they have that one best equation that reduces the amount of error the most, they plug your data into the x-axis and see where you land on the y-axis. And that output is likely to be your credit score when you're approved. Sometimes, though, the bank is not thinking about a dollar amount at all. Instead, they step back and ask a simple question. What is the probability that this person will default within the next year? That is a yes or no question, but they often don't want a hard yes or no. They want a likelihood. For example, there's an 80% chance that this customer will default. And a model called logistic regression fits in here. It starts almost exactly like linear regression by combining your features with weights to get a single score. But instead of using that score directly, it runs it through a sigmoid transformation that squeezes it into a value between 0 and 1. That value is interpreted as the probability you default. During training, the model adjusts the weights of each feature so that people who actually defaulted get scores closer to 1 and people who didn't get probabilities closer to 0. And when it comes to you, the bank will again run your data through the model and let it spit out a probability. This likelihood that you will default within the next year helps them decide whether they will approve your credit card or not. And there are other times when a bank cares less about a score and a limit and more about being able to explain their actions. Regulators and auditors might ask why a specific customer was declined. So the question then becomes, can we create a clear set of rules that separates safer customers from riskier ones? And a model called a decision tree takes that idea quite literally. Essentially, it turns the bank's decision of approving or not approving into a sequence of simple questions. First, it takes a look at all the compiled data of people who were there before you. Then initially, it might split the group based on whether their income is less than a certain amount. With the lower income group, it might then check how many late payments they've had. And in the higher income group, they might check the ratio of debt to income. After each split, the tree is looking for the next best question that separates people with different outcomes. And under the hood, it is measuring which split reduces uncertainty the most and building itself from the top down till each final group at the bottom is mostly high risk or mostly low risk. When the tree is applied to you, it simply walks your data down that chain of questions until you reach one final group. And what typically happens to that group of people is what it predicts will most likely happen with you. The bank also understands that a single decision tree can be fragile, because one odd pattern in the training data can lead to a strange set of splits. So the next question they ask is, how do we get a stable, reliable risk decision even if a tree or two happens to be a little bit off? And to answer that, they use a model called a random forest. Instead of building one tree, they build many. Each tree sees a slightly different sample of past customers, and because of this, each tree ends up with its own rule chain. Some might focus heavily on income at the beginning, some might start with debt ratio, and others might key in on payment history. When you apply, each and every single tree in the forest makes its own decision about you, and the random forest aggregates them usually by averaging or taking the majority vote. This averaging greatly reduces the chance that one unlucky pattern in the training data will dominate your results. The result is more trustworthy, more consistent judgment, especially when the data is messy and noisy. Finally, there are moments when a bank wants to go beyond simple summary features and straightforward rules. At that point, the question becomes, what if the signal we care about when assessing risk is actually hidden inside complicated patterns? This is obviously the most common case, and it is when a bank turns to a model family called neural networks. High-level output is still the probability that the customer will default, but the way they reach that number is different. A neural network takes your inputs and passes them through several layers of computational units. Each layer transforms the data, learning combinations of features that capture more complex patterns than the layer before. The first layer might learn simple ratios or basic combinations, but deeper layers pick up those much more complicated patterns that you might have in your financial history. And during training, whenever the model predicts wrongly, small adjustments are made to millions of internal parameters. Over many passes through the data, those tiny adjustments accumulate, and the network grows into a system that can distinguish high-risk from low-risk customers based on patterns that are too tangled for a single equation. And if you follow this bank scenario from start to finish, you've now learned the 5 most common machine learning methods that are used in real life. So don't forget to save this video for the next time you're confused about machine learning and follow for more.